we're going to spend a little bit of time introducing the concept, or reinforcing the concept, hopefully, of confidence intervals. In this unit, we're going to start trying to use our sample to predict something about an unknown population parameter. And for the beginning, we're going to start with just trying to, and where this particular section 8.1 started, was just trying to estimate the population mean. Now in these works, I'm going to go ahead and use the mean x bar from my sample as kind of our piece that we will work with. I very well could have been using the population proportion and the sample proportion, but for the moment, we'll just work with x bar. Everything that I talk about here applies just as perfectly to the population proportion and the sample proportion. So just be aware of that. And I'm going to use a couple pieces of Legos to demonstrate a couple of important concepts. We're going to assume, among other things, and just to kind of get ourselves going, we're going to assume that we met the 10% rule. If I was working with a proportion, which I'm not this time, but if I was, I'd say I met the large counts condition as well. And should I have been working with a population that was not normally distributed, I'd even go so far as to say that the central limit theorem was met. So we're going to assume that all those conditions, however they might have been required, just depending on what I was working with, will also apply here. And what that in turn translates into is the fact that my sample mean, the distribution of my sampling mean, will be normal with an expected value of, hey, it happens to be mu of x bar, which, since we know is an unbiased estimator of the population, is nothing more than mu. And we'll have a standard deviation for our sampling distribution of the mean, sigma x bar. And what we know, since we met all the lovely conditions of independence through the 10% rule, so on and so forth, I'll be able to say that the actual standard deviation of x bar will be the standard deviation of the population divided by the square root of n, where n is our sample size. Right, so a long prelude there, a couple minutes worth of stuff, but again, just reinforcing a lot of our fundamentals. And so what you see here pictorially is nothing more than the distribution, the sampling distribution of the sample mean. We know it's normal, we know it's mean, which, by the way, since u of x bar is the same as the population mu, we know that our sampling distribution of the sample mean will actually have a mean that matches the population mean. And then what have I drawn here? I've just drawn a couple standard deviations. 2 to the left, mu minus 2 times the standard deviation of the sampling mean. Minus 1, plus 2 times standard deviation, so on and so forth. And if we call with our good old empirical rule, 68% of the data in this distribution lives within 1 standard deviation from the population mean, which also is what? The mean of the sampling distribution. And our good old 95% fits right there. Now, what's this telling us? What does this 95, let me do this just so we can kind of see it. What's the 95 and the 68 mean? Well, remember, there are an incredibly large number of samples that we can do. Remember when we did some of those things on the calculator in class, we saw in our particular case, we could have over 10 times e to the 50th power. That's how many samples we actually could generate. In any case, we could get tons and tons of different values of x bar. And what this is telling us is, well, of all those observations, those individual observations of x bar that we might pull back, 68% of them live, by the empirical rule, within 1 standard deviation of the mean. And what? 95% of those values live within 2 standard deviations of the mean. We're going to work with the 2 standard deviations, what we will call a 95% confidence level. We're going to use this nice little interval bar. That is what you're seeing right there. That Lego piece represents a length, overall length of 4 standard deviations, to the left, to the right. So that's how big this nice little bar is. Now, what you see here in green dots are a whole bunch of possible values that might have come back for x bar for my 1 sample. And we're really asking ourselves, gosh, and we're going to again work from this from the 95% confidence level standpoint. Could do this for 68%, could do it for any percent point, but we'll use 95% confidence at the moment. Well, if my value of x bar has a 95% chance of being within 2 standard deviations of the mean? Well, here's a whole bunch of examples. And what we can look at is, well, gee whiz, this sample mean that came back, look at that. If I go 2 to the left, 2 to the right of that particular value of X bar I might got, it captures the actual population mean. I can do the same thing for a whole bunch of other points. Just kind of watch me move here. Again, I'm touching. Here's another value. Look what happens. My interval happens to contain, it captures the mean. I could do that for these 2 values that I see over here. Again, my bar touches it, my confidence bar. Over here, it does it again. So these are, remember, if you think about it, a good way to describe it, these 1, 2, 3, 4, 5 green dots, they are all part of the what? I'm going to call them part of the 95%. Those are part of the values that I know represent 95%. Anything that's between here and here represents 95% of all values of X bar that could have come back. Well, is this value way over here? Again, notice that where I'm putting these on the y-axis is just so I can go ahead and put my bar down. The height doesn't really have any meaning. It's just the horizontal coordinate I care about. Well, if I go over to this last piece, well, you already notice it's more than 2 standard deviations away from the mean. It's not part of what? The 95%, so to speak. And look what happens when I stretch that bar out. It does not touch the mean. This is one of the possible values that I could have gotten of X bar, which is what? It's not within 2 standard deviations of the mean. Point again. 95% of all the values of standard means of X bar that I could have gotten live right in that range. And so all we're really asking for our one individual observation really is, and again, we're talking at a 95% level for this context of the conversation, is my sample mean value that came back to me, is it part of the 95%? So let's look at that verbally again. And then we'll do a quick problem. So statement. 68% of all values of X are within 1 standard deviation of the population mean mu. 95% of all values of X are within 2 standard deviations, of the population mean mu. And I should really write sigma X bar there, sigma X bar. So let me just go ahead and clean that up quickly. What does this translate to? Well, it translates into the following important piece. Let me just kind of fold my paper up just a little bit so you can kind of still see the normal curve. Bear with me a second. So here's kind of the question I want to start asking. Is my value of X, I'll call it my observed value from the one SRS, the one sample that I happen to do, is it part of this 68%, if I was looking there? Is it part of the 95%? And the answer is, well, question A, I'm 68% confident that, the answer to the question A is, yeah, it is part of the 68%. I'm 95% confident that what? That my particular value of X bar is part of that 95% of all values of X bar that live in my nice little 2 Lego interval world. So, what's that mean? Well, I'm 68% confident that my value of X is within part of the 68. That means it's what? Within 2 standard deviations of the population mean, or 95%. And so what's that telling me? Just kind of turning things backwards for a moment. I know that X bar minus 1 standard deviation from the sampling distribution of the mean, X bar plus 1 standard deviation of the sampling mean above is going to be that 68% confidence interval. And for that matter, if I go X bar, my observed value minus 2 times my standard deviation of the sampling mean, X plus 2 times this number of standard deviations in the sampling mean. There's my 95% confidence interval. In other words, what I was really doing for you is telling you what's the value of this particular piece. Right here at the middle, there's my observed value. Here's 1 standard deviation to the left. There's 1 to the right. For my bigger, my 95% confidence interval, it lives what? 2 standard deviations this way, 2 standard deviations that way. So again, remember, how confident am I that my observed value of X is part of the 95%? And if it's part of that 95%, it means when I lay my lovely little Lego thing that's supposed to go in 2 different directions, 2 standard deviations to the left, 2 standard deviations to the right of my observed value of x bar, the population mean will actually be there. Remember, it's an important point. I have no idea where this population mean is. And so when I get an observed value of the sample mean, I don't know if that observed value is way over here, and that's how I just fit in, or maybe it was way over here. But again, my observation was what? Within 2 standard deviations of where I expect myself to be about the mean, and I cover it. So again, there's nothing that says, oh, I precisely know where a particular value, where my actual x bar value lies. I don't know that. All I know is if I move 2 standard deviations to the left or right of that value, I know that my Lego piece is going to touch the actual population mean. So let's work one example real quick and kind of talk our way through it. I'm going to let my population be defined with the following distribution: normal, with a mean of unknown value, and a standard deviation of 300 units. There we go. I'm going to assume that my population size exceeds 5,000. I'm going to run a single SRS of size 36, and I'm going to obtain, and I did obtain, a sample mean of 1,400. What is our 64% confidence interval for mu? What is our 95 confidence interval for, again, the unknown population mean? Well, again, what are we going to ask ourselves? Is our value of 1,400 part of the 64% confidence interval? Is it part of that 64%? Is it part of that 95% confidence interval? And remember, empirical rule, 1 standard deviation above and below, 2 standard deviations either above or below. Well, how are we going to work this problem? We need to figure out what's the, what's the standard deviation of the sampling mean. And in this case, it is 300 divided by the square root of 36. 300 over 6 equals 50. Now again, size 36, population 5,000. Have we met the 10% rule? Absolutely, positively, yes. We can assume that when we're sampling without replacement from the population with a size of 36, we're much less than 10% of 5,000, which would be 500. 36 is way less than 500. We certainly meet the 10% condition. We can assume independence, and we're able to make this calculation for the size of our standard deviation of the sampling mean. And so, what's that tell us? Well, if I want to go 1 standard deviation above or below, my confidence interval, my 64% confidence interval, is nothing more than 1,400 minus 50, 1,400 plus 50, 1,350 to 1,450. I have 64% confidence that the interval between 1,350 and 1,450 captures the population mean. I know nothing more than that 64% confidence level, which maybe isn't really that great when you think about it, but nonetheless, we'll work with it. A 95% confidence interval is what? 2 standard deviations above and below. I am 95% confident that I am 1,400 minus 2 times 50, 1,300, 1,400 plus 2 times 50, 1,500. I am 95% confident that the interval between 1,300 and 1,500 captures the actual population mean. So it's pretty interesting how we're able to use a lot of concepts, one sample, nothing more than one sample, and the fact that in this case we do know a standard deviation, nothing more than that to begin to narrow our range for what we feel confident about the population mean truly being. So this is what confidence intervals are all about. You might have noticed, by the way, one other piece is as we try to grow that percent confidence, what happens to our interval? It has to get bigger and bigger. Why? Because we need to accept more standard deviations. I'll only accept 1 standard deviation the first go around. 2 standard deviations I need at this stage to be that confident. And for that matter, if I went 3 standard deviations, we'd be talking about a 99% confidence interval. More on that, actually a 99.5% confidence level from the empirical rule. In any case, this is confidence intervals. I hope this helps you out. Don't be afraid to use some of the verbal pieces that I do. Am I part of the 95%? Well, I'm 95% confident that I'm part of the 95%. It's a fair statement, and then we just kind of translate that into what an interval associated with that level of confidence is.